And so you start from some part that you're excited about, whether it's like a particular clicky key or it's like a screen that you saw. My Raspberry Pi story is that I used to live next door at university to Eben Upton, who founded Raspberry Pi. And I introduced him to his girlfriend, Liz, who and I then lost touch with them. And then when Raspberry Pi Foundation was announced, the founding blog post was signed Liz and Evan. And I was like, how many people called Liz and Evan can there be in the world? Another thing that immediately my brain's jumping to is the USB port is over here on the left, but the resistors over here are up here. And so we could go on a big journey around here. But actually, that's just implying to me that I should grab these guys, rotate it around. And now I know that I'll be able to just go straight in. There's my USB traces connected. All right, so can everyone see a big fat Word document or Notepad document, whatever it's called?
Yes, but definitely if you can increase the font size, it's
absolutely. Yeah. So and this is actually just for me to come back to. So I'm going to be using software called KiCad or KiCad, which you can get from kicad.org. And we're going to end up ordering from JLC PCB, but there are lots of different suppliers. So this is just the ones I'm going to use. This is mostly so you can follow along and just so I forget. And actually to one of your, so let's get into the questions. You mentioned it's standardized when I was putting the buttons into the thing. And what's interesting is I think most of the time when I'm designing something hardware, I start from a physical idea. I want some physical object to exist. And so you start from some part that you're excited about, whether it's like a particular clicky key or it's like a screen that you saw, or it's you've got an idea for how you want to do capacitive touch, and or how you want to use 500 sliders. Or in fact, one Christmas I decided I was going to make I don't know if I can pick it up, but I was going to make a keyboard with more sliders and it had musical keys and stupid ideas like that. So it always starts for me with a physical idea. And then what you do is you go and look for the parts. So you start looking online for where are you going to source these parts from? And so one of the things I did when we were talking about perhaps using, clicky keys is I went and Googled who has built, they're called KiCad libraries. It's basically people who've drawn out the shapes for the, and it massively reduces the risk of you getting something wrong. And so that when you physically get the thing back from China, it's likely to fit together. And so I'm using a library from GitHub, which is in this link here, which I've installed. It has instructions on the README, but basically you install it into KiCad and it makes available standard key switch patterns. So that's
a predefined set of things.
Yeah, exactly. It's a bit like it's a bit like using a library or something, and you can absolutely draw them again from scratch, and you'll see that for the screen that I think we're going to use, I've drawn my own one. But if you're using standard parts, it can be helpful to quickly load that. And then there's this incredible tool. So let me show you about part search. So let me just open up a new browser window, and I'll just show you what it's like to. So if we go to JLC PCB/parts. And I'll try and make my browser window a bit bigger. You can search. So, for example, you could say you wanted a 10K resistor and you wanted it in size 0402. Now, everything in electronics is measured in thousandths of an inch. Europeans use millimeters, but
no.
Oh, yeah. So 0402 is a size code, and it means 4 thousandths of an inch by 2 thousandths of an inch, which is basically the size of a human hair. It's absolutely microscopic. It's it's less it's the size of those little parts there, which you don't even that's my fingernail. So 0402 is very small, but it's the standard size for resistors for hobbyist level electronics. They go down to 0201 and then they go even smaller if you're building NVIDIA GPUs or something. But 0402 is a good hobbyist size. 0603 is just about hand solderable. 0805 is easily hand solderable, but the first time you do it, you're like, what the hell is this? This is too tiny. But 0402 is in the realm of I couldn't hand solder it without a microscope. So if I search for 10K 0402, I get back this list of in-stock parts of all the different resistors that I can get. And my pro tip is always to sort by stock. So basically they have 68 million of this particular resistor in stock. And the price is $0.0011, and that's the price to you as a consumer in quantity one. It's quite crazy. That's not even a bulk price. That's like the price when you buy one of these things. which you can just click buy and add it to your cart, like Amazon or whatever. And if we click on this, there's a close-up photograph of it on it with a
Nice.
scale. So that's millimeter squares. And everything has a part number.
Hi everyone, let me take a break to thank members of the show who made this conversation possible. Members get earlier access to videos, including longer unedited footage from live streams, as well as they're invited to our private Discord server. If you want to support this show, there is no better way than becoming a member on YouTube or Patreon. Thank you so much.
And basically what I love is that this company, JLC-PCB, they have a piece of software called Easy EDA, which you can use. It's a web-based design package. I'm going to use KiCad because it's a bit more general and it's not so tied to JLC. But you can use Easy EDA, and they've pre-made the symbol and the footprint, and that's what we're going to do a lot of this today. So do you know what I mean by a symbol and a footprint, or would you like me to? Okay, so the idea of what we're going to do is we build a logical layout of what we want to connect to what, and it's literally like doing a UML diagram or something. Like, I want my computer to talk to the screen, and I want the screen to have this many buttons, and I want these batteries to be here and everything else, and you literally build out a logical description of your circuit using symbols. And then you go to another program. It literally is another executable program. The division is very 1970s, but this is the way it's done. And actually, I'd love to build one of my sort of to-do list projects is to make a handmade. Everyone makes their own editor, right? It's like, I think it's time to make a handmade style electronics program. But in the world of KiCad and EasyDA, they're separate programs. So now you have this footprint, and the footprint describes, and this is actually an SVG file, like you can literally download them from their website, and they're just and the colors have different meanings. So yellow is silkscreen, so they will print that onto your board. It has no electrical meaning, but it's the humans. Red is copper, and that's actually, and gray is solder paste. So they squirt some solder paste down, and then they stick the little tiny resistor on with a robot, and then they stick it in an oven, and the solder melts and flows onto the copper, and now your resistor is now welded to the piece of fiberglass by solder, and you can then draw out the copper in red. And what's cool is the only thing the software does is it's an art package. It's like using Illustrator or a vector art package, but it knows the logical connections, and so it can validate that the copper that you drew matches the logical description of the circuit, and that's everything you need to know. So you draw your logical description, and then you draw your physical description, and the computer has basically it's a bit like having a compiler, and it literally gives you warnings and errors, like the same language as programming. And it says, these two are a bit close. These two bits of copper are not meant to be connected, but they're a hair's breadth apart. Are you sure you really want them to be that close? And that's the process of electronics. And that's everything. I've now described the entire process of what we're about to go through for the next hour or so. So yeah, go ahead.
Sounds easy, but when I've seen like Verilog and VHDL and like FPGA like stuff, like at some point I was like, wait, please, back to software, please.
Yeah. Well, I mean, actually, ironically, Verilog and other FPGAs, they are close to software. But you'll see this is quite fun.
Okay.
And we will do software on the next two. This very much does go back to software. And then the last twist is that. So they've done all this work of making footprints, and historically there was a lot of very busy work of, like, if you wanted to do a design, you would spend half your time at the beginning building out these footprints and symbols and blah, blah, blah. But JLC have done all this work, and then somebody created, this UPeasy person, I think, created a tool called Easy EDA to KiCad, and you give it the part number, and it downloads all of the files from the JLC website, and then makes them available in KiCad. And so the other thing is that, by the way, JLC search sucks. It's really, really hard to find the part you want. So then somebody else on GitHub has created this parametric search, which is much better and more reliable. And basically, they scrape the JLC website. And so you can say, I need a resistor. I need it to be half a watt. I need it, I need this chip. I've heard about this other thing. And this is a more reliable search. I won't bother showing it to you, but that is
part selection is this incredibly time consuming, and originally I didn't think it was important, and I now realize in retrospect part selection is almost like half the battle. You choose your good parts, and then the rest of your life gets easier. So if that's that. And then I also downloaded a 3D model of the Switch of the, so in KiCad you can load in 3D models so that you can visualize what you're building physically. So what I did to speed things up was I went through on KiCad on these websites I just listed, and I found the part numbers for common bits that we might need in the next hour, just to save us basically you watching me on a website for an hour, just like browsing around trying to find a resistor. So this is me doing my sort of homework. So we need a USB-C connector because it's 2026. So I found one, and it's this number. So what I do is if I go and open up a terminal window, and I just run easy EDA. There you go. You can see I've run it lots of times. So you just give it. You want full, meaning I want all the things. 3D model. I want the footprint. I want the stat, and you give it the ID number. You hit enter, and basically it goes and fetches all of the files, converts them into KiCad format, and drops them into the KiCad folder, so that if you're running KiCad, it's available for you to use. So in fact, let's go ahead and grab this USB connector, and we can get started on our journey.
And just to make sure that I have the full picture, if you knew that you wanted USB connector but had no idea what's the part number, you would go to the website and just figure it out through just like a normal human search through website. Okay.
So I would recommend this. You can use so the two tips I would be is you type in USB-C connector, and then you physically look at the photograph and you sort by stock. And if you sort by stock, it's actually, if there are loads of them, it's a really good indicator that this is a popular version. There's like 1 million USB-C connectors, but there's one of them of which they have 9 million in stock. And you're like, well, that's the one everyone uses. And for me, that's become the quickest path to and if there's 5 in stock, that's fine, because you genuinely want that part and you've gone and read the data sheet. So next thing we'll get to is about chips, is everything has a data sheet. So let me just go back to this part thing, and I'll put in the part number that we found. So here is the USB-C connector I chose earlier. But not only have they done the footprint and the symbol for us, they've also linked to a datasheet which the manufacturer would have produced. This one's in Chinese, or a mixture. And basically you just end up skimming through these and seeing whether it's the one for you. And most of the time you don't need to worry about this. But the method I use is, are there millions in stock, 780,000 in stock? It's fine. There's going to be it's going to be a popular thing. So I just started KiCad and it crashed, which I thought was very appropriate. Should we reopen it? Okay, so let's go File, New Project. Anyone want to choose a name? What are we going to call this delightful thing? Wookash thing.
Wookash thing for like a very vague description. I think it's nice.
Okay, that'll do. Yeah.
Whenever you're opening up a window, if you can make it bigger, try. If not, it's gonna be fine. For stream, it might be difficult, but then for the video,
don't worry. This is the opening bit of KiCad, and I'm not going to stay in it, so there's no point resizing it, because this is almost like the front page menu. One thing I will say is there's on the tools menu there's a option plugin and content manager, and that's where you installed the keyboard library that I mentioned. It's listed in the instructions, but just to kind of really hammer it home. And they ship KiCad with a bunch of plugins that they haven't installed, so you might need to go and click them. And the one I always use is there's one called Fabrication Toolkit. And again, this is already there when you download KiCad. You just have to click it and say install. And this is a little script they've written that when you've done all your work, you click one button and now the file, it makes a zip file, literally, that you just upload to China, and then they give you your thing back. So this just removes, again, a lot of busy work. So that's the plugin we're going to use. And I use this one here. If you see me clicking a button, again, this is for retrospect. If you see me clicking at R4 cross, KiCad loves to put little references all over your board, and I think they're messy. And there's a There's a plugin to hide them, so I use that one. So those are the two plugins that I would recommend. Right, we're here. So we have schematic and we have PCB editor. So let's open up our schematic, which is the logical description. And you can zoom in this one, so I will make it big. And let's I've switched on at the bottom left of my screen for people we watching. I've put a keyboard visualizer. So every time I press a key, in the bottom left corner is the key that I pressed. So if you see things magically popping up, you'll be able to see what key I pressed to make that happen. So I pressed A for add.
You're so prepared, Alex.
You're
so prepared, man.
And it does a little circle for click as well, so you can see that. So when I hit paste, I'll just paste that part number. By the magic of that Python script we ran, we already have the logical description, the physical description, and we say OK, and we plonk it down, and I can zoom in for the myopic among you. And there's our USB connector. Now, this is, as I said, two programs. We're in a logical program, and then when I click this little green button up here, that takes us to, it loads up the other executable. And I'm going to basically be bouncing between these two views. So this is the physical, manifestation of the thing. And this little button here is update one from the other. So it copies via Lisp S expressions. God knows why they chose Lisp, but there you go. It copies from the logical description. It sort of reconciles. It's like it tries to reconcile the two states. So I always go from the logical to the physical, but you can actually go the other way as well. But I always, as a habit, go from logical to physical. So I say update PCB, and now it's placed the USB connector physically in the thing. And you can see the little pads, the little copper red bits. And even cooler, if I go to the edge cuts layer and draw a rectangle, that's basically the fiberglass. That's why it's green. So if I draw a nice big green rectangle, I now have a physical board with a USB connector on it. So if I press Alt-3, I can see immediately what I've made. And obviously that USB connector is not going to be very easy to plug in. So I should probably move it to the edge of the board. So I can grab it, M to move, R to rotate. And again, you'll be able to see after the fact. So there's our little USB connector hanging off the edge of the board. And it's really easy to... I had an idea. I've never done this before, but I'm going to make a banana for scale. Because you forget, so if I draw a yellow rectangle and I E to edit it, and I'll say, how big is a banana? It's like...
How big?
30 millimeters wide and 100 and... Oh, you can type for millimeters and it will convert it to inches. So if you're not... you can do maths in here as well. It's really nice, actually. So you can do 10 times 2 minus 3 millimeters. Or you can do 10 inches minus 2 millimeters plus... it's quite crazy. But let's say it's 111 millimeters. Is that banana sized?
That's 10... No, that's too small, no? It's 10 centimeters. So it's...
let's go bigger.
Twice. 2 times that.
200 millimeters? Okay, 200 millimeters. So healthy banana. Okay, so there's our banana for scale. And that's a long banana. But yes, so my point is we can come back to this banana later. I'll just write banana for scale here. Hang on. Banana for scale. And for scale. There we go. And we'll do it. Bold, knockout. There we go. Little knob for the banana there. Beautiful. So we have a banana for scale.
One noob question. The physical view, I understand, right? You have a physical thing, and then you mentioned that the colors matter. Red is copper. This I get. Then the logical, why don't... I know that it's sort of the historical artifact that you have two views, but the logical one. What do you do in the logical one that you cannot do in the physical one?
Good question. They're written by different people with different user interface shortcuts and different vibes and different grids. Yeah, so a lot of the answer to that question is historical accident and nothing very good. But it is actually useful to be able to... I'll give you an example. You can make references to disparate nets. They're logical things that should be connected. So let's say we have 5 volts, which is the power coming into the system. And that's going to be all over our board. We physically want that to be all over the place. But what you can do in the logical thing, and we'll do it right now, actually. So let's just grab this X to flip in the X direction. the shell I'm not going to connect. So this is debated amongst people, but if you have a metal enclosure, you should connect the shell of your USB connector to the metal enclosure, but we're not going to have a metal enclosure, so I'm going to just, you can ground it as well, but you can go and find flame wars online about what one should do there.
Maybe one will be in comments.
Yeah, exactly. Yeah. So W makes a wire. So let me say there's a ground here and there's a ground down here. Now I could choose to connect them together with a wire. So let's make a wire there and another one here. And again, you know, if things look like they're happening magically, look in the bottom corner and you'll see what key I'm pressing. And P is for power symbols. So I'm going to add a ground. And again, I will actually post this online afterwards, so you don't have to go through this from scratch. So this is the sort of symbol for ground. I'm saying that's going to be our 0 reference point. Now I could choose to do it that way, and that sort of represents the physical reality if I'm going to want to wire those together. An alternative way of doing that would have just been to have the ground symbol, and do it again here, and because they're both labeled ground, logically they're now connected. And in the physical view, we're going to have to draw a wire between them. But in the logical view, I can just label things. So another example would be V bus is going to be the power coming in from our bus, and let's give it a label. So I can give it this flag and I call it B bus. Actually, no, I'll use a power thing, B bus. Yeah, there we go. It's just convention, but I've just labeled that V bus, and I'll do the same down here. Okay, and then there are some of these pins that we don't actually need, so I'm going to just be neat and put a little cross next to them. Where's my cross thing gone? Okay, we don't need SBU2. That's for God knows what, some fancy Thunderbolt crap probably. And let's do a wire between. They have, so you know USB-C is reversible. So they actually have pins on the top and pins on the bottom. And if you want to build a fancy thing, it can actually know which way around you've connected, and you can do all sorts of fancy things. But we're dumb and simple. So we're just going to connect the ones on the top to the ones on the bottom. And again, I could have used symbols to do this, but I think it's cuter to do it with little, little things. Let's make a label on this one, and we're going to call it DP for data positive, and attach it to the right place. There we go. And then for negative, we're going to do, data minus. I think they call it M. Do they call it M or N? N, data negative. Okay. So I've logically labeled that these two pins should be called DN, and these two pins should be called DP for positive and negative. So that's the data coming from the computer. And then CC is a little USB-ism where basically it allows you to negotiate with the computer, with the host, how much power you're going to draw and how intelligent you are. Now, if you're very intelligent and you want 20 volts and 100 amps and, very powerful thing, you actually have to connect a microcontroller to these wires, and then it enters into a negotiation with the charger, and it's all very fancy. But in simple devices, you can simply pull these down to ground with a resistor. And the spec for USB says the resistor must be 5.1 kilo ohms, and your Mac or whatever you plug it into will measure that resistance and go, aha, it's a dumb device, I'm going to pull this to ground. And so a USB-A to USB-C cable, for example, will have these two resistors in it, because USB-A didn't actually have these resistors, they added it for USB-C. And famously, Raspberry Pi used one resistor for this, and as a result, the Raspberry Pi was not compatible with half of the chargers out there, and they completely messed it up. So the price of like 0.0001 cents, they accidentally. So let's go. Yeah, so let's go and find out. I have a part number of a 5.1K resistor, so I can just grab it out of the. Let's call this 5.1K. All right, so we've got a 5.1K resistor, and we're following the data sheet that we haven't read on stream, but which said, "Thou shalt not draw more than 500 milliamps if you do this." So now we've connected two resistors, and we've connected them to the ground, and we've basically announced we want 500 milliamps, please, which is plenty for a small little device. So if we now go over to our physical view and we press the update button, it attaches to my cursor all the things that I made, which is just 2 resistors. And I've selected all, and I'm going to use that little plugin I mentioned to get rid of all of those labels because I find them ugly. And I'm also going to get rid of the fab layer as well. So now it's just nice and clean.
Nice.
I don't have to be in pain. So now it's M, and I can move it around. It's showing me that I want a connection. I hope you can see these very faint lines, but it's basically saying, please, please, please connect. Change my grid size to be a bit smaller. Please connect X to make a trace, that one to that one. So now I've drawn some copper. I literally, just a drawing program. Don't be afraid, it's literally just a drawing program. I have drawn a piece of copper from my little chip. And if we look in 3D over here, and we zoom in, you'll see very faintly that there is actually copper underneath the mask connecting the things. That's all there is to it. So we're basically going to do this times infinity, and I might copy paste some things to avoid you all going mad. But we'll see. Now, what to do about ground? Because everything wants to connect to ground. So how do you think about electricity? Like if I said to you, like, what's on these wires? What's the meaning of the what's a voltage? Like what level do we begin from?
I mean, we can't go too deep, I would say. Like, for example, we could have asked why there are 2 resistors, not 1, for example. Right.
Oh, that's
so,
good.
like, but I think we kind of need to have like a base level of like some level of understanding, and then just
So the analogy I have in my mind, which isn't perfect. Some people say, they're just voltages and they're magical, and you can think of them like ones and zeros. If you're doing digital design, you can think of a high voltage as a 1, and these are all true. Yeah. Everything I'm about to say is true, but it's sort of like layers of understanding, and we're not going to get to the bottom one. And other people say, no, it's like pipes with water in it. But that, I find that difficult, because then it's like, well, what's the difference between current and voltage? And like the analogy I like to have in my head is a wire is like a channel, like an open, imagine a little stream, like an open topped tub that I've literally drawn the shape, and the voltage is how high the water is. So a high voltage, the water is quite high up in that channel, and a low voltage, the water is low down. And some devices, like things that do work in the world, like LEDs that light up, or heaters or motors, or they actually need the water to be flowing past them downhill effectively to sort of turn a little water wheel. So those devices, speakers, to do physical work, they need current, they need the water to be flowing. But what's interesting about most digital design is they don't need the water to be flowing at all. You can imagine there's a smart little computer called Bob, and he has a pin that he wants to send a signal to somebody. So he has a channel going over to that somebody, which is maybe, I don't know, a GPU, and he wants to tell the GPU to draw something. So it sets a bunch of voltages on its pins. But because it's digital, what it actually does is it fills up the channels with water. And what the GPU does, those channels are actually closed, and it puts a tiny pinprick. The GPU has this tiny pinprick and sort of just sees whether or not any water's dribbling out and goes, okay, the water level's high. Okay, I'll make a decision. I'll draw a different color on the screen or whatever. So interestingly, with digital electronics, very little current is flowing. So you're actually just setting the level of this in this tank. So every time I'm drawing a copper wire, imagine me drawing a little open tank, and the voltages are basically filling up this tank to high or draining it down to low. And what's interesting is, how does it drain it down to low? Like where does the water go? And or how does it fill up? And this analogy actually isn't perfect, but it also gives you an intuition for a bunch of weird things. So people say, well, you need capacitors, and there's reflections, and you might need impedance matching, all these mystical terms that you don't need to worry about. But imagine that you had a tank and you suddenly filled it with water, because you're a CPU and you want to tell a GPU to draw something in red. So you need to absolutely fill up this tank with high now. So you pump as hard as you can the water in, not because you need to flow into the GPU, but you need to rapidly get that tank to be high as quick as possible. And to do that, you need to pump a load of water in, and then there'll be ripples, and literally the physical ripples they'll reflect off the end of your tank. So they'll be bouncing around, and the water level will be doing this. And that, all of that is literally what happens in the electronics. And so when you hear about interference, EMI and stuff, it's because you're pumping these quite drastic transitions of level. There's quite hard work. You have to sort of pump water in and pump it out very quickly when you want it to go down. And to get to my point, the way it goes down is whoever's doing the pumping ultimately has to drain that water back to the source of power, the battery or the USB port or whatever. So when we want to drive something from high down to low, we need to pull the water out of whatever tanks it's in and suck it back, and it literally will all flow physically. This is a physical, very physical thing. The charge on the electrons will flow back through the thing and ultimately has to make it back to wherever your reference point is, your ground point is, which for us is going to be a USB or a battery. So ground is this thing that everyone ends up being connected to, but it's the way that they drain. It's where all the stuff you don't want anymore gets drained to, and that's why ground is such a sort of ubiquitous point of connection. And so with these two resistors, you said, why are there two? Well, it's a bit weird, and it's basically so your Mac can sense what it's been plugged into, sort of understand the USB device. And what it does is it tentatively puts a bit of water onto these two pins, and there are two because the USB port is swappable. So it can tell which way up. So I can have different values on the different things, and that means different things. So if I put a small resistor here and a big resistor here, it means one thing. If I put two big resistors, it means something else, just by convention. So the Mac tentatively puts some water in, measures how quickly it fills up, goes, oh, there's a big resistor there. It's not quite how it works, but for the sake of argument, and then it drains down to ground, and it's basically measuring the current. It doesn't matter the details, but the point is, the reason there are two is because by convention they want two equal things, and that means 500 milliamps. Whereas if you had one big and one little, it would mean something else. So it's like a convention in the USB standard, 1,000-page long thing where some wise person has decided that that's the convention. So we have to connect everything back to ground, and my pro tip is immediately that you have a ground. What you want to do, we're going to make the entire back of our board be a big ground plane, a big fat piece of copper, and that way we don't need to think about ground anymore. So all I'm going to do is I'm going to draw a trace with X and then push V, and V makes a via. Now a via is literally a robot comes along with a drill and drills a hole through the board, and then they plate copper through the hole and out onto the other side. So it's just a way of connecting a piece of copper on the top to a piece of copper on the bottom. And we are just going to design that all of our grounds are immediately going to go straight through to the back. And now I don't need to think about ground anymore, because I'm basically going to just wash the whole back in copper. And so every time I do a ground, you'll see me, and you can shout at me if I forget to do it. And the compiler will shout at me later if I forget to do it. But we're going to just connect everything.
So it's like every time when you want to have a connection to ground, you just want to go to the other side of the PCB. Yeah.
Okay. But that's what I've chosen to do. Yeah. And I'm suggesting that's a good idea. And so I can actually do that now. So I can take this thing, which is a polygon, which is showing a little sort of filled polygon, and we're going to draw over the shape of our entire board. I can be very rough with it. I will say, I want to be on the front and the back. So red is copper on the front and blue is copper on the back. So I'm going to draw this plane. I'm actually going to say only on the back, and I want to connect it to ground. I say okay, and I'm going to draw a giant rectangle. Blue is the back, remember? And double click. And so now it has filled the entire back of my device with copper. So if we look in 3D again, I can flip it over and you can see it's a little bit lighter because it's all covered in copper. And here are those tiny holes that the robots are going to drill for us. It's quite remarkable, really. I mean, these are like absolutely microscopic things. And they've, I think the 3D model actually has the copper kind of going through it, but the camera control is too annoying there's actually copper on the inside of these things. Yeah, you can see it's a little bit yellow. So that's basically connected. All of my my ground points are now connected together. And if I wanted to, I could actually make that be the front as well. So I could put copper all over the front and all over the back. And one of the sort of brilliant things about these design packages is that it's figured out, this polygon has been cut out. So the red copper has been automatically is avoiding all the places it shouldn't touch, but it's flowing into all the places that it should touch. So here it's realized the copper can flow onto the ground and into this little thing, but it shouldn't touch any of these other signals because they're not ground.
Super smart.
Yeah. So if I drew another trace here, and another trace here, and another trace here. And I have to press B to refill it. It will carve out. I don't know if it uses STFs under the hood or some horrifying geometric CSG library, but it's carved out where the copper goes. And again, we can see that in the. Oh yeah, here we go. So you can see that it's made copper traces, and then everything else around it is not connected. So does that all make sense? Is this a moment to pause and check that? I don't know if is this live? I don't know if this is live or whether people think
yes, this is live. There's people. Wait, there's question, but let me attempt to answer and then double check on the answer. Is ground the place where we wedge? Is ground the place from which we get the energy or send the energy back? I'm assuming it's like depending on how you design the PCB. Right?
The weird thing is it's so. In the end, there are always currents. So I mentioned the GPU is needing to sense whether the water level is high or low, and it has a tiny pinprick hole. That pinprick hole was there in the story because actually, in order to, it's a bit like Heisenberg or something, in order to know the water level, you have to look and you have to allow a little bit of water to flow. And so in the end, everything whenever you want to do something with electricity at the bottom level, like the transistor nuts and bolts of this, there will be tiny amounts of current flowing around, and it's the movement of that current that allows you to measure things, switch transistors, make motors go, and so electricity always has to flow in a loop. So you'll have some chemical agent or power thing like a battery that's basically a pump that pumps water up from low level to high level, and then it goes around your circuit and goes through a pin and basically magically goes into a chip. But what's actually happening is very small amounts of that water will actually be flowing into the chip, coming out and going back round, and it wants to find a way back down to low. So these are potential energies. It's where the water analogy starts getting a little dodgy, but high water is the same as being at a high potential energy, and low water is at a low potential energy. It wants to roll downhill. So the electricity will just inevitably roll downhill, and ground is by convention the point of but the funny thing is you can have negative potentials. So where the channel analogy breaks down is ground is not empty or something. Ground is just some height that we've chosen that is literally physically referenced to the ground, on the earth. But you can actually have potentials below that, so you can have negative voltages. And so, for example, ground is almost like. So, is ground a place where energy? Yes, the current will flow back to ground by convention, because we're drawing loops basically, but we forget about half of the loop most of the time. Most of the time we're thinking like digital engineers, and we think about high and low, and we forget that there's actually current flowing, and ground is almost like where that current flows to, but we don't think about it. We always have to have a loop, and electricity won't work unless there's a loop going around, and ground is just a quick way of digital engineers going, and everything goes to ground. It's almost like, oh yeah, I know there's loops, don't worry about it. It's just like everything ends up going to ground. So it's a convention. I was going to say, I think in the early 19th century, the Germans, because electrons are negative, I believe they had ground as the highest potential, and then they would actually hang everything negative. So all of their circuits are sort of upside down in some sense, because they thought in terms of ground being the highest potential and then everything being measured negative to that. And that made sense because electrons are negatively charged. I don't remember, I'm not a historian, but a lot of this is convention. So the modern convention, if you like, or the kind of de facto winning convention, is that ground is in some sense 0 volts, and other levels are measured above that. So a high signal, logical 1 signal is measured as like 3 volts above ground. But that's a convention. You could choose to have logical 0 be ground and then have logical 1 be minus 12 volts below ground if you wanted to. And then all the currents would just flow in the opposite direction, but it would still work logically. So it's slightly a leaky abstraction, or like an API boundary thing of like, you don't need to think about currents anymore. You can just think about logical 1s and 0s and highs and lows. But the reality of the situation, I'm trying to give you an intuition of what's happening under the hood, is that there's little bits of current flowing around, and they always end up flowing back through ground and back to your battery, because otherwise nothing would actually happen. Does that answer the question? Or
yes.
Okay, cool. I'll just join the
Do you remember that we had to draw the negative and positive together? So I just quickly joined those together. So this is the data from our USB port, so we can pull that out.
But shouldn't they be automatically joined if you made the connection in the logical?
Interestingly,
or you just assigned
I just assigned them. So it's labeled them. It's assigned a label. So it knows that this one is VBus and it knows this lower one is VBus, and it knows that they're not connected. So if I were to click the compiler button, the check button, which is this one up here, I can say run design rules check, and it will basically say, oh dear, VBus and VBus are not connected. So I'm clicking on it. It's telling me these two things are not physically connected. So then you're like, well, why can't it connect them? And the answer is it could, and that's called auto routing. So what we're doing here is, but we're making sort of design choices like, do we want VBus to go around here and then down here and then we go up here? We could get artistic. We could have VBus go through another layer of copper, or we could have a thick trace. And one thing I've forgotten to do is you can set up predefined sizes of, so let's have an 8mm trace and a 12mm trace. So now I have two predefined sizes of trace, and I can press W and Shift W to cycle between my traces. This is a convention. It's just a drawing program. But all these choices, it's difficult for the computer to immediately make because it doesn't know that VBus is going to be carrying X amount of current. It doesn't know the details of your design. You could imagine a program where it did, and perhaps there'll be future. But in the world of KiCad and the world of today, of this program, in front of this stream, it won't connect it automatically unless you ask it to auto route, and auto route just do a horrifying job. So open problem.
What would be the difference for the thickness? What would change?
So that's the sort of how much resistance to filling. If you imagine that channel, a big fat trace will have more capacitance, have more capacity. Literally, it'll take more water to fill it, but it's also easier to fill it. And so when you're powering your thing, there's a few special traces. VBus is power. That's basically the thing that's allowing your transistors to switch. And they'll be drinking from VBus in order to do their work, and they'll get hot. And that's what makes your chips hot. And every time you switch a transistor, it gulps down a little bit of energy in order to fill or drain whatever of these channels are connected to it. And so your transistors are like switches, and they're opening up a channel to either ground to drain it down, or opening up a channel to VBus to fill it up again. And they're basically, so all your millions of transistors, and literally we will have millions of transistors because we've got a CPU on here, they're switching away. And every time they want to fill up a trace, they have to gulp down the current from VBus. And so if you have a million transistors all gulping at once, then you have quite a big current flowing. And so, a little chip can be drawing 100 milliamps of current, which is like the amount of water that's flowing. So it's helpful to have nice fat traces. And again, remember the banana for scale. So when I said, like my healthy 12 mil thick thing, it's still like, very, very, very tiny. It's not healthy. It's not a really fat piece of copper, but it's just convention. Also, it's helpful to know that your power traces are a little bit fatter because it allows you to see them more easily. So let me show you a little bit more of a circuit. So over here off camera, I have should we do I know what we'll do. We'll get a bit less abstract and let's do something. Okay, sorry, slight change of plan. I mentioned that when you design something, you sorry, I've lost the view. Okay. I start from the physical layout. So I came across this screen that I've never used before, and I bought it from Amazon this morning and then plugged it in and it didn't work. But I'm just going to ignore the not workingness. And I drew a it's got 7 pins on it. In fact, I'll show you what I found. Let's go open it. Come on. Here we go. I think it was, something like that. I just searched for like 1.3 inch screen TFT something, and this came up. And I'm like, okay, that looks pretty easy to use, and it's like $6.99, and if you buy it from China, it's like 50p. But if you buy it from Amazon Prime delivery, thanks Jeff Bezos, you can get it for the
10x markup and have it with you tomorrow and then not be able to use it. I was like, fine, let's use that. But that didn't exist as a KiCad part that I could find. So I quickly drew a logical description of it. And here's my screen. It's got the 4 mounting points in the corners and it's got the 7 pins. And I gave them the same names that were printed in the Amazon listing. And if I go over to the physical layout and do the update dance, I also drew I went and got the data sheet and I physically drew rectangles, just very boringly, sizing the rectangles to be, as big as I wanted. So I could rotate it around. I could say, okay, we're going to have our screen and we're going to put it sort of there. And we're going to move this stuff up, maybe in the middle of the screen. Let's refill those things. And that now defines, let's flip it over to be on the other side. So I press F, inconveniently moves it to the top. There we go, let's move it back down again. So I've now flipped that onto the back side. So here we have a screen on one side. And I just Googled for 1.3 inch TFT step 3D file, and someone had modeled it for me, so I didn't even have to model it. So I didn't do the 3D modeling, I did the 2D modeling. Okay. So now we have a screen on one side and our electronics on the other, and that's perfect. And it's super rewarding to do some. That one part allows us to sort of imagine our widget. So now I can resize the green board. Let's make it a bit bigger vertically and refill that copper. So now we're starting to get a sense of the physicality of the device. So then, should we shove the key switches in the bottom? We could do that.
Is it now like 90 degrees rotated? Like,
yep.
It's not going to be in the middle now, right?
Yeah, I mean it's a bit off center. It's a square screen, so the visible area is that lighter grey rectangle. Yeah. So we could adjust. I love your bit OCD.
It's a bit of OCD. Yeah. Exactly.
So there's a measurement tool here. So we could say, like, what is the distance from here to here? 375 mil. And I'm not OCD, so I tend to make things very slapdash. So 375 mil is out to about there, which is at 2655. Okay, so I need to edit this rectangle and I'll make it go out to 2655. Oops. Okay. So now the pins aren't in the middle, but the viewable area.
Yes, now you can feel it.
Yeah, okay. Yeah, I like it. The annoying thing is that the mounting holes of the Chinese pre-made thing, I don't know. It's fine. Let's go with this. That's good. These are the compromises. The other thing we could do is we could go and source just the actual flat panel and not buy these pre-made modules. That's totally doable as well. It makes the construction a little bit more complicated. So one of the advantages of using a little pre-made module is that most of the electronics can be assembled for us in China. Then we get the board back, and then all we have to do is solder in very crudely these big fat metal posts, which is trivial to do for even someone with my blind eyesight. Whereas if we you can just about see under here the flat flex. If you can buy just the glass and the little tiny coppery flat flex, and then you have to get solder paste and So I'm making a conscious choice here. But if you were making the tiniest possible thing, then you would make different choices. So there's our screen. Let's quickly finish off the physical design to show you there's not much to it with by adding the switches. So I remember from that library that I mentioned I installed, there was a Choc V1 solder, which is, again, we're going to hand solder it. So it's just a logical and physical description of a switch. And we're going to ground one pin. So let's ground that pin. And let's label the other one button 1. So now we have a switch that's literally, the drawing is kind of redolent of what it does. It's a switch that normally these aren't connected, and when you push it down, it's going to connect whatever we logically call button 1 to ground. So that's all there is to a switch, and clearly we want 4 of these things. So we go 2, 3, 4, and we'll rename this one. There's probably a slicker way to do this, but I'm going to manually. There we go. So we've labeled our 4 buttons. And if I go to here and I say update, I wish I knew the keyboard shortcut for update. what is it? F8. Okay, well, I need to memorize F8. Now here are our 4 switches, which it's brought in, and I just move them out of the way. So let's move number 1. Oh, I can say T. Okay. Flip it onto the other side of the board. About there. Flip. Rotate. Now they've drawn conveniently these rectangles, which are the spacing that you'd normally have on a keyboard. So if I abut these perfectly, then that will have the natural sort of spacing of a. So the physical key is the blue rectangle, I believe, and the natural spacing is. I'm not a keyboard enthusiast, but I believe it's called 1U. So this one's this one. Hang on. T.
You're not a keyboard enthusiast, and yet you made a keyboard. Keyboard.
Well, that's for you. This is the first time I've used these. This is the first time I've used these things.
But you mentioned the musical.
Yeah. I meant.
Oh, you meant like the huge. Oh.
I mean like that. This was fun. This was like 80 little tiny sliders, and musical keys. Anyway, that's I meant I'm not a mechanical keyboards enthusiast, although I do have a couple. Right. Anyway, sorry. Do you
have a couple? I'm not an enthusiast, but I have a couple.
Do you have it? Well, do you have a mechanical keyboard?
I have. Actually, we were talking about this with Anton yesterday on stream. It's like he also had like a mechanical keyboard. But like, if you have a couple, then you're already like at least like a level 1 enthusiast, no?
Yeah. Okay, I'm a level 1. Okay, I'm level 1. But you can all judge my keyboards. Like, here you go. They're not plugged in, which is part of level 0. So here's number 1. I don't even know what that is, but people can tell me if that's a good keyboard or not. It's got linear keys, so it's a bit soggy. And then this one is called the divorce machine because it's really clicky and it makes my girlfriend want to divorce me. So I don't use this one because it's too noisy. But that's my there you go. That's my unused keyboard piles. Okay, so I shoved those 4 puppies onto the board. And what's exciting for me at this moment is that when you go and look at I forgot to flip 2 of them. Did I forget? Yes, I forgot they're on the wrong side. So there you go. Schoolboy error. We've invented an amazing new machine with buttons all over it. It's like one on top. I don't think we want that. I mean, we could do that.
I mean, if you have a gamepad, you have both. Like here, you have some, but you also have some keys down, like on the other side. So actually, it's not that. It might be super smart.
We could do. I mean, we could do that. We could have. We probably can't. The problem is they'd interfere with each other if we tried to. So this is another reason the 3D view is actually really useful because you can sort of see when physical bits of plastic are going to interfere. The classic thing is you get lost in the logical world and you build this thing, you get it manufactured, and then when you come to plug it all together, it's called interfering. The bits interfere with each other, and like bits of plastic can't go through each other. So I'm gonna keep it simple for now, but yes, we could absolutely have these on the other side. So that I feel like that's the physicality of the device, and the rest is all just little teeny tiny bits of electronics to join, USB power to the rest of the thing. I'm going to stick a microprocessor on it next, just to demystify that, and then from there we might copy paste some elements, but just to kind of run you through a bigger chip, because we haven't really done chip yet. I feel like it might be interesting to demystify, what it is to put a processor on there. And you can buy modules, so like Raspberry Pi sell. Like Arduino, you may have heard of Arduinos, and let me show you this. So you can buy these little boards, and then you can stick them onto breadboards. And this is a cool way of getting into electronics without needing to solder, without needing to do any of this PCB design stuff. But I know what it is. I find it infinitely more satisfying to. It's like the handmade aesthetic. I think it's like, do you use a Python library or do you use a STB single header library? And if you want to, you can go and be an assembler programmer or a force programmer and make your own chips. But it's like choosing your level, right? And so I've done this. I'm not dissing this at all. This is awesome. I also write Python code, and sometimes you just want to be able to pull something off the shelf, plug it in, and go without any sort of manufacturing step. But the process of getting the CPU exactly as I want it, with the wires connected exactly how I want it, and then get it manufactured, to me is a magical, mystical, wonderful thing. So we're at that level. We're arbitrarily at that level, in the same way that, arbitrarily C programmers using header file libraries. It's a level that we like, and that makes us feel happy and at peace. Yes. So I don't know if I'm at peace or not, but
it's
okay,
like now you already have like your everything has a part number. You already know what you're doing. Like, I guess this process would look a little bit different if you were like, okay, what's the part number? Searching. Okay, I can't find it. What is this garbage website? It's like, it's
I mean, I lost many hours to searching and learning how to find stuff. I mean, when I started my journey, the assembly process wasn't cheap, so I would actually make the boards in China, but without any of the parts, and then I would buy the parts from Mouser or DigiKey or these other things, and then I'd solder them on by hand. And I just didn't enjoy it. It was a fun craft process, but it was too slow, and the iteration time was too long. So it's, again, choose your poison. So I've definitely accelerated some things here, but GitHub is amazing. There's so much open source hardware, and really what I wanted to show in the stream was like, none of this is hard. All of this is like enjoyable. It's like almost like a soccer band game vibe to it, of like you're just messing around. And let's get to that, actually. So I'm waffling, sorry, I'm talking a load of rubbish. All right, we've got our screen, and my schematics always look like chaos. Like you mentioned OCD before, like you can get neat, you can have multiple pages, you can draw little legends, and you can say like, here is the screen, and comment your code and make it beautiful and have tabs and spaces and things. That I just vomit everything onto the page in a random order. It's not very well organized. Okay, chippy time. So we pay A to add, and I think the part number is C2040, which is the Raspberry Pi. I always thought it was cute that they managed to get JLC to choose a part number that matched the actual thing. Okay, so this behemoth is a CPU or a microcontroller, dual core, as I mentioned before, 256K of RAM. And the reason I chose to do this one next is like, do not be afraid. This is just very much a case of going through. I'll make some room for it, if nothing else. And we're just going to go through methodically, and we're going to fill in the pins we want. Now, the ones on the right, the way they've drawn the symbol, again, this is logical. So someone has drawn this symbol. I don't know who it was, whether it was someone in China or someone at Raspberry Pi, but they've chosen to group the pins logically. And they've put all the ones on the right are called GPIO, which stands for General Purpose Input and Output. And that basically is like whatever we want: sound cards, screens, buttons, LEDs. So that's the fun stuff is going to go on the right. The stuff at the top is juice going in. The stuff at the bottom is juice falling out the bottom to going back to ground. And then the stuff on the left is housekeeping, that you have to go read the data sheet and follow the rules. And so you just do a little bit of housekeeping. You get those. You can think of these like the API or the config file. So the stuff on the right is whatever we want to write, userland, exciting. The stuff on the left in this for the symbol, because it's been neatly done. I mean, sometimes they jumble all these pins together and it's nightmarish. But whoever did this symbol, hats off to you. This is like your config of like, how do I want this chip to be, and it's actually pretty simple. So these, what should we do first? Yeah, actually, look, here's one we can do already. You see this DN for negative and DP for positive on the USB. I just select those, copy paste. Well, look, okay, the person who did this did it in M rather than N, but we get the vibe. So this is the USB positive and USB negative. And so all we have to do is wire these together. Now, in the data sheet, it says, please put a little tiny resistor in there to reduce reflections. And so you just do what the data sheet said. But if you have in your head that trench of water mentality, what happens is your PC sends a rush of a 1 or a 0 down the cable, physically down the cable, and it lands at your microcontroller's pin, which wants to know whether it's high or low, and it literally bounces off the pin and reflects back. And by putting a little teeny tiny 33 ohm resistor is what I think they call for 28, but I'm going to go for 33 because it's cheaper. So we add one of these. So I just say A, paste the part number. There we go, and change that to 33 ohms, so I know
So 3 ohms and be a little bit neat so that Wookash doesn't go crazy. And there we go. That's number 1. And actually, let's just flip it. There we go. So we've now done USB. That's it. Logically, we have now connected USB to and this is the wonderful world we live in. Like, these chips are so easy to use compared to 80s or 90s. They've put all of the IP. They've licensed someone's USB IP and shoved it into their chip, and all I have to do is essentially wire up a couple of wires to a couple of resistors, and I now have USB connectivity. And when we get to the software stream, it'll literally be like, I can do printf over USB and have it show up in the debugger or whatever else. In fact, that reminds me, the debugging port's very cute. So let's just quickly do that because that's similarly easy. And down here, I have a header. There we go. See. Ask me a question while I do.
In the meantime, yeah. So you mentioned that, like, hats off to the person who designed this, and like you have like on the right things you worry about, like care about, and like everything is like nice structurally around designed. Is this? I guess it's not the case for other microcontrollers, right? Like,
the Raspberry Pi one is actually famously nicely designed and. In terms of friendly to the user. Like, that thing when you're designing an API and you're like, you can tell that it was written by someone who was thinking about the call site. A bad library is someone who's thinking about their problems, internal problems, and they expose it in the API. And the Raspberry Pi guys or girls have found, to their enormous credit, they're thinking about us. We're at the call site right now, and we're like trying to wire in USB, and they just make it super easy for us. And that extends to documentation as well. So if I quickly go over to Chrome, and if you do RP 2040 datasheet, their datasheets are amazing. They're just so well written, and that's one of the reasons I use this chip. It has a lovely C++ SDK as well, C SDK as well. Not C++, but you can use it for C++. Has a really, really nice C SDK. But the documentation is great. This is 642-page datasheet, and this is just about the hardware, not about the software that you would then write upon it. And they go through all of the structure of the chip, how it works, every register, every pin in beautiful, beautiful detail. And then, because that's not enough, you do a search for like the design guide, and this is a 30-page document, and this is basically saying, okay,
a high-level thing.
Yeah, well, this is the physical design of, like, this is how you should think about designing it. Maybe you want to think about power supply when you're laying it out. Maybe lay it out this way. You don't have to. If you want to do flash storage, which we're about to do, maybe think about this. And it's so. This is not how every chip is documented. I mean, they do have this documentation, but it isn't presented in a beautiful 37-page nugget of a PDF. And that's one of the reasons I love this chip so much. Is that, here you go, so USB. So they said use 27.4 ohm resistors, and I use 33. That's because 33 is a common size and 27.4 is the less common size. And they even say, make sure they're close to the chip. And we can feel good about ourselves because, well, I've only done it logically, but I've drawn it logically close. Let's go be good people. And F8, I didn't remember the button. So now here's our CPU. Here's our programming header. We'll shove the programming header up here somewhere. And now they said, please make sure it's close to the chip. And now KiCad's showing me that I want it to be, I don't know, we'll put it where? Will be nice, and we'll put it. And the reason you physically want it close is because this is addressing a physical concern, which is reflections. When you hit the different impedance of the pin, blah blah blah. So the channel, the water spills up.
Exactly.
So that's why they literally will make physical. That trace is too fat, so it's bigger, thin one, and I've managed to. Even that's too fat. Okay, let's be careful. That one. Okay. Oh, there we go. Sometimes it's a bit picky about, and then this is where OCD can really come in. It's like, Alex, it's not symmetrical. You've got let's just turn off the fill. You've got a kink in your wire there. So I was like, okay, I'm sorry. I'll just.
That's terrible.
Yeah, no, that's okay. And then I'll pull this one down, and you can get really kind of it's like sort of therapeutic. You just sit there and you kind of line things up exactly as you want them to be. And these horrifying reference designators. Oh, look, there's a bug in the
Python script. There are bugs in stuff. See, come on. Oh, for goodness sake. Oh, that's annoying. That's a bug. Quick to
You can't go to the 3D visualization?
No, it's the stop having references everywhere. So this U2 thing.
This one.
So there's something in here. It's probably one of these. If I click on it, and it's got some formatting bug, and the Python script that this button is erroring. So let's have a look at our 3D view. So we've got our programming header, which I'll put just inside a bit further inside. There we go. Doink. So now we have our little processor and our two little USB things, and we're going to need to connect these two little copper wires over here on the left to those. We're not actually going to do that on stream, or I don't know. If you want to be here for 5 hours, we can be. But but first, I wanted to show you the flash RAM. So one of the interesting choices they made is there's no flash storage on this chip. Some chips you buy them and they have like a mega flash storage, or and you can just put the program onto them. So you put the firmware onto them and they remember. And Raspberry Pi elected to leave that to you to put in a separate chip. So one of the bits of sort of housekeeping you have to do is you have to hook up a flash chip to this these set of little pins. And as usual, it's the same dance. So I have I chose a Winbond flash ROM because Raspberry Pi recommended them. There's a big one or a little one. I'll go for the little one. I think it's 2 megs. You don't need more than 2 megs of this isn't memory. Remember, this is almost like the drive, the flash drive of the thing. Now, whoever drew this chip doesn't get my love, because why is it so wide? There was no reason for this chip to be epically wide from a logical point of view. That's just irritating. Let me just move.
Does it reflect the physical size or not?
It does. I think the chip's probably quite wide. I don't know. Whoever drew it was having a day. God knows what they were thinking. Now we have to hook these up. Let's flip it in the X direction. Let's see if that lines up better. That does line up better. Okay. So I happen to know that what they call CS, Raspberry Pi calls SS. IO1, one button. IO1 wants to be IO. SD1, IO2 wants to be. These are different companies that make these chips, right? So they're slightly different conventions. Clock. Keep hitting the wrong key. W. Okay, W for a wire, so it's come around to a clock. And again, I could have labelled that clock and then gone and had a label over here. Yeah. But my taste is that I like to, when it's a one-to-one point connection, when there's not there's not a tree structure or something, I tend to just draw the wire, because I think but other people will shout at me and say, no, you should label every single wire so that it's clear. But
oh, really?
Yeah.
But
sorry, guys.
It's as if you wanted to send event for just instead of calling a function.
Yeah, exactly. Oh, it's like me calling variables I instead of loop count iterator 17. It's like life is short. Hold or reset. That's IO3. Okay, so that's this guy is coming on here. I'm being a little bit cautious. I know you're watching. You see. So there we go. So there's our thing, and then VCC is conventionally means power. Sometimes it's VDD, sometimes it's VCC. I'm sure there's historical reason, like everything else in electronics, but we are going to power this from 3.3 volts. So we grab a power indicator and we say, right, we're going to, now at some point we'll have to design a circuit that, that thing's getting in the way. Let's move this out of the way. Again, this is just cosmetic. It can overlap as much as you like, but I'm just, that's horrible. Let's move this further away. Where am I going to put you? Over there. Okay, there we go. 3 volts, 3. So that's the juice going into the RAM chip. And while we're doing juice, we can do juice here. So Raspberry Pi have 2 different. They need 2 different voltages. They need actually all the way over to here. They need 3.3 volts on these pins. So I shall just hook them up. And so different bits of the chip will basically, drink upon the power. So there we go. And then they also want 1.1 volts. So power.
I wonder, because you also have your previous experience, and now you also done this prototype. So you're in a very good spot to do this from memory. But how much time would you like? Imagine like a multiplier that I'm trying to find. For like,
If you've
you're here for like hour and 30 minutes doing this.
Yeah.
How much time would it actually take?
The AIs can't yet draw circuit diagrams. They think they can, and you can ask them, how do I connect this up? And they'll get it horribly wrong. So they're good at reading data sheets, and they're good at suggesting connections, but never ever ask it to attempt to draw a circuit. Even when you show it a circuit, it gets confused and starts rambling. So AI is not a help yet. The thing I'm skipping out, and if you've never used a part before, the multiplier is 10x or more. Because what you end up doing is reading that 37-page data sheet carefully and saying, okay, and so to give you an example of that, I just said, oh, this is 1.1, this is 3.3. And how did I know that? Well, Raspberry Pi, as I said, has done a good job of, here we go. Where's that design guide? Pip assets, what terrible. So somewhere there'll be power, input, supply. So here you go. They've got their 1.1 volt here, and somewhere in the text it will say, by the way, blah blah blah, you need to do this and this and this, and you need to, and this is they're describing that we're going to need this many capacitors of this size, and you just go read them, and like, so however long it takes you to read the 37-page PDF, sort of internalize it, and then it's not hard. The point is it's just reading, and it's very nicely written, and the actual mechanical process, a bit like coding, is very repetitive. You just do it, and if you've used a part before, the multiplier goes down to maybe 2x, and if you've used a part this week because you were preparing for a stream, the multiplier goes down again, to 1x. But it's time consuming, but it's actually sort of simple and easy and quite sort of, as I say, sort of relaxing in a weird way. So I feel like I've done all my homework up there. I've done my homework down here. I've got my programming header, which I put in while you were chatting, and this is an ARM. This is a company ARM made a convention, and so there's a whole library of little programmers. So I have one that happens to be made by Raspberry Pi, but you plug it into USB at one end, and it has 3 wires. This one is 3 loose wires, but as you'll notice on the screen, I have a connector with 3 wires. I don't know if I have the cable, but there's a standard cable that fits into that connector, and by convention, and those 3 wires are enough that your computer can take over control of the thing and do breakpoints, single stepping, read RAM, poke RAM, reflash it. And so basically this is like God mode. This is the sort of God mode. It's called SWD, serial wire debug, I think is what SWD stands for, or something like that. I think it's actually serial wire data and serial wire clock. Okay. And the overall interface is called SWD, I think. I don't know. Anyway, God mode port, which you don't have to put on. You can use USB and faff around with, when you have to put a pin into your USB router and you reset it. You're basically forcing the thing to wipe its firmware and reboot. You can do the same thing with this thing and then flash it from USB, and it takes ages. But if you want to be able to debug it and have a good iteration time, which you do, trust me, it's worth putting a little God mode jobby on the side. So we're nearly done. This one's super easy. Run. This is a they specify 10K for some reason. So let's just do what the Raspberry Pi. My Raspberry Pi story is that I used to live next door at university to Eben Upton, who founded Raspberry Pi, and I introduced him to his girlfriend Liz, who and I then lost touch with them. And then when Raspberry Pi Foundation was announced, the founding blog post was signed Liz and Evan. And I was like, how many people called Liz and Evan can there be in the world? And it turns out that it was Liz and Evan. So I am Cupid of Raspberry Pi, so I'm biased.
You basically made it, like you can, you're the author.
Don't let Liz or Evan hear that. But yeah, they're lovely people. But I knew them long before Raspberry Pi. I knew Liz at high school, actually, and that's another story. But run. So in this pin apparently makes the chip go, and if you want to stop the chip from going, you can ground it, and it will just stop going. If you want it to go, you can make it go high. Now we quite like our thing to go, so I'm just going to connect it to high. And again, in the 37-page PDF somewhere, it explains why the hell you'd want that, but. I believe in my notes I just said, where is it? Just double check that I'm not doing this wrong. Here you go. blah, 5 caps, blah, 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 run 10k high. There we go. Okay, fine. It's saying, so I mentioned poking a wire, poking into your USB router. So what was the thing again? 10k high. Oh, interesting. Okay. I didn't believe myself. So what I'm saying is that somewhere else in that document is I have to do the same thing to the SS line. I don't know why it's called SS. Now what that's doing is when the chip boots up for the first time and it's like awakening from its factory slumber, it looks at this pin and it looks to see if it's high or low. And actually this pin is really for talking to the memory. So later on, it's going to have a different function, which is to go and talk to the memory chip. But at the moment of like awakening and dawn of man and all that stuff, it looks, and if it's high, it says, okay, I'm flashed, I'm ready, someone's put a program onto me, I'm going to run as usual. So we pull that high. But if it's low at the moment that power is applied, it means that the user is poking the pin into the thing, and it should be reset to a little ROM that Raspberry Pi flashed onto it. It goes into it's called UF2 mode, and basically it presents itself on the USB as a little drive, and that's all built into the chip, like no software required on our part. There's a ROM in there, which is open source, and you can read the source code on GitHub. But there's a ROM baked into the chip, which when that pin is low, it will start running that ROM and has a tiny little USB thing that runs a little fat file system and like allows you to flash the thing. So that's like your panic. This is the panic button, basically. Now we could put a physical button on, but that costs money. So I'm going to put, and it's only ever used for panicking, right? So instead I'm going to do what's called a solder jumper. So let's grab this and move it out of the way. Ooh, that's ugly. Hang on, less ugly. So this solder jumper is literally a piece of metal on the physical board. I'm just going to give it a shape. So let's say solder jumper. How big do we want to make it? We want to make it solder open. Let's do 1 millimeter by 1.5 millimeters. Okay, I think I did that right. I was going a bit too quickly, sorry. Yeah, so now if we go over to our physical world and we update. Oh, there we go, yeah. So there's a couple of extra resistors I've put in, I don't know why. But here is our solder jumper, and we're going to put it somewhere near the SS pin. Where's the SS pin gone? Up here. It's actually physically huge. That's 1 millimeter. This giant rectangle is 1 millimeter across.
Okay.
So scale, you get used to losing scale. But if we look at that on the physical thing, it's all gold and shiny. So what that will be is I don't know why it doesn't look quite right. It should have a break in the middle. Have I chosen the wrong? I know I might have chosen the wrong shape. 1 second. Let me just double check. Let's go. Bridge, is it? No. Open. Solder. I'm trying to remember. Solder jumper. Is it open? That's not quite what I expected. View. Yeah, I don't know why that's. I don't think it's a solder jumper I want. I think I want something else, but I can't remember what it's called. Solder bridge, solder. I know, hang on a second, I've got one. Here's one I made earlier. Let me go and grab. 1 moment, please. Oh no, that is the right one. Okay. It looks a bit dodgy to me on the 3D view, and I'll double check off the stream. But
yeah, we can.
To me, it looks like there's copper there, which I don't think.
Can you tell me how would it work instead of a physical button?
So you will have to get a pair of tweezers or a paper clip, and you will have to physically connect those two pads together, and then you power the thing up, and it goes into it. So you have to bridge those two. So the idea of a solder bridge is it's like two little pads that are physically visible on the board, and you can take a pair of tweezers or a tiny piece of metal or a tip of a screwdriver, and you press it against, and then when you power it up, that will pull that wire down. The Raspberry Pi will notice and go into panic mode, basically. So that's the concession to panic mode. So this is what I mean by sort of doing your homework, so then I catch it up and so on and so forth. And where's our memory chip? So here's our memory chip. Now I just want to quickly show this one because this is fun. An example of Raspberry Pi doing a good job. So
I don't know why I'm turning this into a Raspberry Pi fan stream, but I promise it's not.
It's kind of like a Raspberry fan stream now, a little bit.
Yeah, that's okay. I'm okay with that. Look at this. They've laid it out so nicely. So I didn't lay that out very nicely, but there we go. It's like a nice little hook, and then come on, no, there we go. And sometimes KiCad insists on messing up your beautifully laid traces, but
looks like pipes.
Yeah.
Nice.
And obviously I could have. It's a bit too far over, isn't it? Let's move it. Something that's going to mess up my. Yeah. So this is why you can obsess over this for like days, because let's get it a bit neater than that. That was a bit too ugly. No. There we go. That's better. We've got space. We don't need it to be tiny, but I don't know why it's not keen to connect. Normally it's a little bit more. You can't feel it, but basically it's resisting jump. When it's happy, it jumps into the. No. Just trying to be too clever and go around. No, I don't want to go around there. I'll come up here. Sometimes it's just frustratingly dumb. There we go. And so look at that. They know that you're going to need to hook these. Oh God. There we go. They knew that you're going to want to connect a flash chip here, and they know that the standard flash chips have a certain layout, and so they make it easy for you to just do a good layout. Like, boom, that was easy. And I'd say that you'll notice there that I was moving things around. So if you're doing this yourself and you're learning and you're placing these things down, people often obsess about building up their full circuit diagram in the logical view. And it's a bit like doing your entire API design on paper without ever having written a line of code. I would highly recommend against doing it that way. Instead, what I'd recommend is doing a little bit by little bit, just as I've been doing, hopping back into the physical world and thinking about the physical world bit by bit, and getting a good trace, a good route. Is more about where you put the islands, the chips, and then the flow of the wires becomes really nice. So when I was beginning, I'd have like 500 chips, and I'd start like boshing them around here, and then suddenly I have to like connect all these traces, and I'm doing all these traces, and it's just a mess. And I learned the hard way that what you actually want to do is gradually bring the things and arrange this is why it's like a soccer band game or something. You arrange the pieces neatly, bit by bit, and you grow it out. So for example, another thing that immediately my brain's jumping to is the USB port is over here on the left, but the resistors over here are up here, and so we could go on a big like journey around here, but actually that's just implying to me that I should grab these guys and rotate it round, and now I know that I'll be able to just go straight in, and there's my USB traces connected. And again, I should probably line it up more, but I won't bother. And likewise, I'm like, where am I going to put my programming header? And Raspberry Pi have chosen to put the programming header pins on this side. So I could put this here, but it's going to get in the way. It's going to physically interfere with, if I look on the other side, it's going to physically interfere with those soldering pins of the screen. So I'm starting to make design decisions, like physical product design decisions of like, I think I will leave it up there, and I'll just turn the corner, and that's not going to be too, that's not going to be too hellish.
This, if you do this like piece by piece, you kind of have the time to do a bit of a refactor and like go step back and do it. If you have like everything at the same time, you can feel just overwhelmed with the complexity, right? At some point.
So do you want to? We could skip to the end. I have one I made earlier. Well, how would you like to? So this refactoring idea. What that makes me think about is that's absolutely almost. I'm teaching how I would do this. I'm self-taught, as I said, but I've also been around the self-taught mill a bunch of times, and I learned this the hard way, that like when you're young and excited and whatever, and you've never done it before, you sort of dive into too much of like, you think you know what you want, or you think you know what the design is going to be. And what I've found is that like doing it bit by bit starts changing the vibe, and you're like, I've got space over here on the board, I could put something physically there. And so I mean, I could show you where I got to with this design.
Yes,
In
I
order
think
to
we can.
skip ahead, or
I think we can do it. Like skip ahead this process because it's a little bit, I guess, like tedious in terms of like
it's
doing
repetitious.
the actual work.
All right, so let's do that.
We can open then the other one, the schematic you ended up with, and do a bit of a review, like what's going on.
Yeah, exactly. So, I mean, this is where the schematic ended. It's not hugely different from where we were a minute ago, which I think is worth kind of noting. So down here, do you remember I put those 4 switches in and I labeled them button 1, button 2, button 3? Well, here they are, exactly the same switches. And I've also added these LEDs. And these LEDs are actually really beautiful. They're that you give them power juice in the top, and they drain to ground like everyone else. And then you feed one wire in to give it the color. And you're like, well, how the hell does that work? Just one wire, not even the clock. And it's quite amazing. What it is that you give it a pulse, and if it's a short pulse, and by short, I think they have a tiny little, not clock, but they're manufactured with intolerance to sort of have a sense of time inside them. So they know, which is actually quite a hard thing to do without an external clock. So you give them a pulse, and if you give them a short pulse, it interprets that as a 0. And if you give it a long pulse, it interprets that as a 1. And why didn't you just give it a high or low? Well, because it also has a memory of 24 bits, 24 being a suspiciously color-related number. And what it does is that memory is arranged in a thing called a shift register. Do you know what a shift register is?
Oh, is this going to be like... Wow, that's
so you give it a 1, and all the memory, it basically mem copies the memory over 1 bit and puts the new pulse in. And then if you do it again, they all shuffle over and the next bit goes in. And then here's the crazy bit. If you then go quiet and don't send a pulse for like 2 pulses length, like, its clock times out, goes, okay, no more data. It then takes whatever's in its memory and it physically puts it onto the RGB LED and physically becomes pink or green or red or blue, depending on whatever RGB value you just shifted in. But it gets wilder because that 24-bit memory this is where we're feeding it in on the left. They expose the bits that fall out at the other end after 24 bits fall out of this pin. And so you can wire it to the next LED and then wire that one to the next LED and wire that one to the next LED. And then they fall out and fall onto the floor. The electrons fall onto the floor at the end, and never mind. So the cool thing is you can shift in all the colors for all of your LEDs and just keep going, like 24 times 4 bits, just fly into this thing, and it effectively scrolls through all of the LEDs. And then when you stop, they all go, okay, and ting, and all the colors come up. So with one wire and one connection to your computer, but you have to have ultra precise timing. So if an interrupt happens or ESP packet happens or a task switch happens, your LEDs go, oh, he's done. I'll take the colors and I'll latch them. So these are almost impossible to interface to with a big computer.
Is this called pulse width modulation?
No, it's it's not called that, but it is the pulse widths play a role. Pulse width modulation is typically when you want to express an analog signal like a sound, and you don't have analog electronics. So what you do instead is you have a pulse whose width you modulate, say PWM, and you go from a very long pulse to a very short pulse. And the interesting thing is that on average, the amount, if you blur your eyes and look back, the average voltage is the analog voltage that you would have wanted. And so Class D amplifiers, if you go and buy a fancy hi-fi or even a headphone amp, they'll typically be a Class D amplifier. And the reason it's called Class D is because they just have 2 very fat transistors, and one is for going high and one is for going low. And when it wants to send out an analog audio waveform, it does what you just said, pulse width modulation, and it switches on and off these transistors, but they're fully on or fully off. It fully pulls it to the top, fully pulls it to the bottom, which means that it doesn't consume as much power as trying to analogically balance this. So like holding a voltage at precisely 0.32 volts is actually quite hard. It's like a tug of war. So a class A amplifier literally has 2 analog transistors playing tug of war, trying to hold the voltage at the precise right level to make your speaker waggle and play the drum and bass that you want to listen to. Whereas class D is like, no, I'm going to go all the way to 1 for 10% of the time, all the way to 0 for 90% of the time. Right, that's 0.1 volts now. And then you shove it through a capacitor and you smooth it out, and your speakers, and you get analog. So that's what pulse width will do. This is something else. This is like pulse width for sending data on a single line. I don't know. It's not quite the same thing. Sorry, you asked a long answer.
Yeah, I picked it up from the chat. Somebody mentioned this PWM. Nice. Okay. So this was LEDs, right? The added LEDs near the buttons.
Here is the CPU and the same. So interesting. So this is a cost thing. I was like, I don't want 10k resistors. I'll just go with 5.1. All I'm having to do is pull this up to say go. It just doesn't need to be precise. So I happen to have 5.1k because Mr. USB told me I needed precisely 5.1k. So I've paid for someone to go and load the 5.1k resistors onto the robot. I don't want to pay them to go and do a 10k. So Wozniak, Steve, was famous for like tricks where he would reduce the bill of materials and the number of different parts. And this is a 0.0001% Wozniak game of like, like you just. So here's the thing I was doing before of like the pull up and the panic button, all the same. Here's a crystal oscillator. So the USB spec again also mandates 48 megahertz. You have to be exactly 48 megahertz. Both sides need to talk within quite a close tolerance. And so this little piece of piezo ceramic thing is there to provide a precise time base to the whole system. So that's more bookkeeping. This is an accelerometer. So to give you a sense of like how simple it is and why it's Lego, I did the part search. I Googled for accelerometers, and this thing is like 2 millimeters by 2 millimeters, and it's very cheap because of phones. So thank you, phones. And you literally drop it into your circuit, and you have 2 wires called SCL, clock and data. C is always clock, D is always data. And you just wire them up. So I've labeled them, and somewhere here on the Raspberry Pi, I have just put them in. And then you just follow the data sheet and do your homework, right? So it's like, please give me a big, nice capacitor here and give me a small capacitor here. So I was like, okay, data sheet, I'll do what you told me to do. And that's it. So implementing an accelerometer is literally drop a chip using A, find the part, draw a handful of lines as you've seen me do, and we're done. That's an accelerometer done. Tick, next thing. This is the screen, which I've labeled up the pins. I didn't bother labeling it before. What's this one? I've never used this one before. This is a bit of a punt in the dark as well. I asked ChatGPT, what is the cheapest, most common built-in speaker amplifier, digital sound card, sound blaster in a chip, please? And it was like this one. It's like, okay, so I just went onto GLC, and so you feed in digital data in there. Power, ground, power, not connected, more power. Please can I have a capacitor from the data sheet?
But this is for playing sounds? No.
So I'll say in a moment. Yeah, I want my little thing to be able to play music. Like, let's have a speaker. And then it's like, plug your speaker in here, speaker minus and speaker plus. So I don't know, we'll have to go find a little tiny speaker and we'll solder it in. Ground, not connected, clock, and bit clock. And so it turns out that these 3 wires are the digital interface to the CPU. And when we get to software, that basically in this hardware design mode, we're like, that's software's problem. That's next week's problem. All I have to do is connect LR clock, B clock, and audio to pins on the, there they are. So I've connected them to the CPU, pins 7, 8, and 9. Job done. Now, that will cause us pain in the software thing, because now I have to go and remember that pin 7 is the data, pin 8 is the bit clock, and pin 9 is the stereo. The LR clock is basically you go low for left and high for right. And that's why it's called LR, left, right. And B is bit clock. Every time you have a bit of data, you clock it. So we're going to have to write software to waggle these pins in just the right way to make this chip happy. But I can wear my hardware designer hat and say, don't care. That's software's problem now. So there's a sound card, done. And again, very simple. Now this mess up here is also a bit risky because I haven't tested this perfectly. This is a battery charging USB power delivery system from Texas Instruments. And I was like, I want a cheap, widely stocked, this is my, as part search mode, is like, I have a 3.7 volt battery, I have USB, and I want to be able to charge that thing. And is there a chip that does it? Of course there is. So I just dump it down and I follow the data sheet. So you plug the battery in to these two pins here, and then this is all just literally reading the data sheet. In fact, let me show you the experience of reading this data sheet. So a non-Raspberry Pi data sheet. So we just go to Chrome, we say, oh, sorry, I'll do it in this window. That data sheet. Yeah, that'll do. Texas Instruments. Here you go. Standalone, 1 cell, 1.5 amp linear battery charger with power path. And then it shows me what I have to do logically, typically. And then you go and read the rest of the thing. Or if you're me and a bit of a cowboy, you're just like, well,
whatever,
it'll probably work. So I just, I did read. So basically, I was like, what is this ILM pin? So you go and find the pin definitions. And here you go, ILM. Adjustable current limit programming. Connect a 1100 to 8000 ohm resistor to program the maximum current. The input current includes system load and the battery charge current. If you leave it unconnected, it disables all charging. It's like, okay, well, we're definitely going to want to connect that. Let's see what I chose. I chose 1K, which is actually outside the range of the ones that they said 1100 to 8. So I'm slightly out of spec, but, YOLO. So I shoved that in. And actually, when I built the little one as a prototype, I forgot the on-off switch. So it didn't occur to me that we might ever want to be able to switch it off, which is a bit embarrassing because when I was soldering it together, it suddenly switched on. I was like, oh God, how do I switch it off? And it was a nightmare. So then I read this data sheet more carefully and I realized it's actually BQ2407X, meaning some other number. And then it turns out that there are 5 possible different numbers. And this is an example of a badly written data sheet. It's like, well, what's the difference between these? This table is so useless. All of them are the same package and the same, like, how is that useful? That's so dumb. And eventually somewhere in here, you find a table, here you go, this one, where it tells you what the difference is. And somewhere in this table, it says these ones have a optional function called sys off. And I was like, oh, that sounds handy. I need to be able to switch the system off. So then you go and search for like sys off and you find there's the pin, yeah. System, when the input is out, blah, blah, blah. And you basically just have to go read it. System enable input. Connect it to turn off, blah, blah, blah. So I basically read this and I was like, okay, this is the power button. So what you do is you pull it up to the battery to keep it off. So counterintuitively, when this is high, the system is off. So I was like, okay, Texas Instruments, I don't know what you were smoking when you made this, but we will pull this very weakly high. So the battery pulls this high to keep itself off. And this is a giant resistor so that I don't drain too much of the battery. So the entire time it's sat in your drawer not being used, a microamp or so, 3 microamps of current are actually leaking through this wire just to keep it switched off. And then these two are connected to the microcontroller to pull it down to ground. In other words, to say, switch yourself on. And one of them is the physical button, the big fat chalky button that we have. So basically physically pressing the top left button will switch the thing on. So for the moment that you press that button down, this thing will come to life. It'll power everything up. The CPU will boot. About a millisecond later, our code will start running and it'll go, oh God. And the CPU will then program the CPU to pull this other pin down to 0. So this is under our software controls. The soft power's down here. And then you release the button physically in that few milliseconds, but by now we've taken over and we're keeping ourselves alive by pulling soft power down. And whenever we want to power down in software, we let go of that. We let that go to high again. And now this chip will power us all down. So I've never tested this. This is purely a theory from reading the data sheet. We will find out in a week or two when the boards come back from China.
Yes.
Whether or not soft power works. So like the prototype I have is always on. never off, and the battery will just drain. But this is my solution to that. So that's it. That's literally the whole review of the schematic. And then physical land looks very, very similar to what we had before. But
it's a bit busier, no?
Yeah, but it's the same thing, right? So here's our where was that? We did that little chip. Do you remember I was doing that, and I've ended up with it on the bottom here. So there's the sort of flow of, and you can see that I've coloured all the grounds green, just as you can ask for a particular connection to be green. So everywhere that's ground. Oh, there's an example where I haven't pulled that down to the other side. So let's shove a wire in. So I'm trying to remember to physically close to every pin that wants to be ground. I plumb a little wire through to the other side of the board. So when we look at it in 3D and we switch off you can see that almost the entirety of the back, there's a few places where I've had to use wires to carry other stuff. But almost the entirety of the back is, so this whole flat piece of copper is ground. And so all these little peppered holes are places on the front side that wanted to be ground. And and these ones actually just wanted to go over here. So let me explain that. So the buttons, there's button 2, button 1, button 3, and so there's 4 buttons. They come up to this river up the middle. But unfortunately, they need to hop over the power line, and they needed to hop over the USB lines. Do you remember we did DN and DP? So I basically nip over to the blue side, sneak up the middle, and hop back onto the front side. So I've tried to minimize the amount and length of those traces. I think there's one other place where
Can you see it in 3D?
Yeah.
This hopping over.
Yeah, so the 4 buttons are coming from the bottom here and these 2, and they go up in a river, and then they come up on the other side, and then they come over here, and then they come out and they go into the CPU. Okay. So a good design will have very minimal layer hops, and it isn't because hopping layers is actually bad. The electricity is quite happy to go through these little holes. They add a little bit of inductance, a little bit of resistance, but it's actually not too bad. The main reason they're bad is because, do you remember I said current always flows in loops? So like, although we don't think about it, we think of just highs and lows. Whenever so for example, we were talking about those pulses that we send to the LEDs. These are the white things of the LEDs, and they actually shine through a hole on the back. So they physically cut a hole in the fiberglass, then they solder the LED down, and then the light shines out on this side, so that then when we put the switches on top, the switches are made of clear plastic, and the light shines through the switch. Anyway, so we're sending these pulses through, but actually that takes energy, right? Like empowering these LEDs takes energy, and that has to flow back through ground to the USB port. So you want literally as nice a journey for the ground return current to rush, and if it can't make it back to home, it will go the most direct route. So for high frequency signals, they actually follow the sort of path of least resistance, if you like. Actually, the path of least inductance, but it doesn't matter. And if it crosses over any other signals, it will actually leak a little bit of noise into that signal. So every time you cross over these wires, it's better to see it in the schematic view. So this is a USB signal, and every time these USB data, you know, when you hear your phone going tick, 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 that stuff, it's the sort of moral equivalent of that. That will be coupling onto these blue wires. But luckily, 1, it's not analog, so it's not very fast, it's not going to matter. And 2, these wires are actually the buttons, which are these incredibly slow, dumb human speed. You know, they go down for like seconds at a time, and then they go up for hundreds of milliseconds. And so a little bit of chatter crossing over, is not too bad. But if you have sensitive signals crossing over each other, or even analog signals, audio signals crossing over each other, that's where you get noise. That's where, you know, you plug in a bad USB audio device, and you hear like, or you open a browser window and suddenly your speakers go bzzz. That's basically bad PCB design. That's currents flowing through ground, because people crossed over there, they crossed the beams, man. Don't cross the beams, don't cross the streams. So that's it. And it is, as you can see, it's more busy, but it's just repeating what I did before more. I think this probably took me 4 or 5 hours to lay out fairly carefully, not having done all the chips before, like, discovering those datasheet things. And if I'd never done any of these chips before, it might have taken me a day or two.
And
yeah.
Can we do a bit of a review / prep for the software part? Like what is there that we will be able to use, like from the software side of things?
That's a great question. As a bridge to that, let me show you what happens when we manufacture this. So I mentioned that there's a plugin. There's different plugins for different manufacturers, but this one's JLC's plugin. So the Chinese company called JLC. And you just click a button, you say generate, and it opens a folder called production with a zip file. This is called testy because I wasn't intending to actually manufacture this. It probably has bugs and I'm not actually going to click buy, but I can at least show you the process. And that'll take us to software and the process is gloriously slick. So you go to Not Parts, you just go to their website. Obviously this is slick because this is how they make money. And you hit order now and it just says add Gerber file, which is basically the file format of the thing. And I just drop it on there and then it gets uploaded to China.
Nice.
And okay. And it shows me their rendering, so you can sort of confirm that they've interpreted the file correctly. So we can click on it and it will give us a web-based view, slightly different colors, but conceptually, and I've put a bit of effort into some silkscreen stuff, and so that's looks good to me. So I say yes, I can choose a color. So I think I will make it purple. So now it's purple, and I would like it to be golden rather than silver. And you can choose lead or lead-free. If you're German, you must choose lead-free. It's illegal to import leaded solder, I believe. Or and Enig is lead-free and gold finished. Slightly more expensive. Notice the prices though.
Can you increase the size? Yeah.
So the price of the PCB, this is for 5, by the way. Like the minimum order quantity is 5, I believe. Yeah, 5. So we could order 10,000 if we wanted, if we were confident. But five will do.
Product.
With medical grade. No, we don't use medical grade. No, I don't want industrial. Oh, consumer's good. Okay. The price is $2 for 5. And the gold finish cost me $16, so it's a bit of a luxury. Let's not do that. Let's go back to lead free. Lead free is going to cost me $1.
Wow.
I can poison myself for free. So that's the PCB. So that's just the fiberglass part. That's not the robots placing. That's a rather nice color. Okay, fine. So we say yes, and then we say please engage the robots and please assemble the top side. And unfortunately, the LEDs are so-called standard assembly, which jacks the price up a little bit. If you choose very vanilla parts, the robots are happy. But if you choose fancy parts, like the accelerometer is teeny tiny, has higher precision, needs to be placed by the fancier robot or something. So I have to use not economic assembly. And if I click the wrong one, it would just tell me later and be like, you've used a part that's expensive. Would you like to upgrade?
What would be the economic price?
Well, let's start with economic and see. So let's go with economic, and then we just say next, and it shows me the board, and it's like, yes, that's still the board. And now you add the bill of materials. Now let me just show you. Oh God, I think it was called. What path is it in? Production. Okay, so it's under here. It was my second attempt at the hardware. Production. I don't know why it didn't remember the. So it's just a comma. It's just a spreadsheet file. So if we actually look at it in, does Mac have a quick view for? Yeah, here you go. It's literally just a spreadsheet that plugin wrote out, listing out all of the parts and what their footprint is and how many of them are and what their value is and crucially what the part number was that we were selecting. So that's that. And then and this one is positions. Solo Tech is literally a text file with for each part its X coordinate, Y coordinate, rotation, and whether it's on the top or the bottom. And so we will add that. And then we say process.
And Which is bill of materials, right?
Bill of materials. And it says that the chock switches don't exist because they don't have JLC part numbers, and the test points, which are just test things, that's fine. It's like, don't worry about that. It's just warning. It's a warning, basically. It's like, are you sure? Now here it's saying standard only. So the LEDs 1, 2, 3, and 4 are standard only. So I'm only allowed to manufacture those. And I think the other one is the accelerometer. So if I'd chosen a different accelerometer, I might have been able to avoid standard. Okay. So that's another example of like the part selection process. You can start thinking about what would be cheaper. Let's keep going and say, no, don't place them. So I'm going to keep the cheap price. Do not place this part. So it's basically...
So technically you would get to this without the parts that would violate the economic...
Yeah, exactly. So now the LEDs are missing suspiciously from their web view. So here's what they think the robot's going to assemble. And basically this is them having parsed the CSV file and pray that they got the angles right. And the crazy thing is there are bugs. There's a lot of human labor that went into the footprint libraries and stuff, and there are just bugs everywhere. So what you have to do is pink dots are where they believe pin number 1 is, where JLC believes it, and white are dots that I put onto my silk screen by hand to where I believe pin 1 is. And manually with my eyeballs, I have to check that all of the pink dots match a white dot, give or take. Or if not, does that make sense? So
yes, but it doesn't make sense. You had a CSV with positions for everything. Like you have all the data in the program.
No, but there's a convention of where 0 is or which way up is, and guess what? Every part is different. So here's one that's gone wrong conveniently. Oh god, it's right clicking over on the trackpad. Look, here's a part. Sorry, this part here is meant to be sitting on these pads. So I have to manually rotate it with the space bar and then nudge it over.
Oh, wow.
And say, okay, that's where I want it to be. And that's a bug. And I can go back and edit my footprint and where the origin is. It's literally just like, this is like Unity Y up versus Unreal Z up, whichever way around it is. It's literally that. So whoever drew that footprint disagreed with whoever drew it at JLC. And the only data that's passed between them is X, Y position and rotation. And so if they have a different idea of where 0 is, then so you basically go through, and most of the time it's correct. And even better, this is absolutely kudos to the Chinese engineers. A human will look at this and they will do this step for you as well. In fact, there's so much here that's wrong. Look, all these resistors are off. Now, some people I know are like, YOLO, doesn't matter. They'll fix it. And they rely on some guy to basically manually go through and do this for every single mistake. And actually, this is the most messed up a board I've ever seen. I think I might have accidentally pushed a button and shifted the whole board. I think I might have nudged, because it isn't normally this bad. So something has gone wrong in that normally, but it's been useful and instructive to show you. This one is actually rotated wrong. Anyway, so you go through and you fix it. And normally that takes me about 30 seconds. There's normally 1 or 2 chips that are wrong. For some reason, almost everything on the board has gone horribly wrong. But let's just say YOLO next, like loving it.
If I would be doing this for the first time, I would be so freaked out now. Like, did I make everything wrong? Like I had it all there, like nicely in my schematic, and now it's like everything's all over the place. What's going on? Like,
now this is interesting. So the price is actually less good than it used to be. So
really, they jacked up the price?
So this is for 5. This is for 5.
Yeah.
So divide by 5. So we're getting $8 to set the thing up. That's to plug the robots in. This is a fixed cost. This is a fixed cost. So if we were ordering 1,000.
Can you zoom in?
Oh, sorry, yeah. So hang on, let me try the squiggle plus. Their website is one of these very JavaScript. No, it's not letting me. It's not letting me scale.
But
okay, there we go.
There's a loop. Okay, no, that works.
No,
this one.
Yeah, it wasn't behaving. I know it is. Okay, fair enough. Most of these are single one-off prices. So if we were to order 100, these numbers don't go up.
Yeah.
So the setup fee stays $8, whether I'm doing 5 or whether I'm doing 1,000. $1.50 for the stencil. It's not large.
these are the component prices. That will scale with the number. But actually, there's breakpoints where like the more you buy, the cheaper they get. So that will probably go down by a factor of 2 or 3 once you get to 20. And once you get to 100, it goes down another factor of 2 or 3. This is a one-time cost. This is evil. Basically, every time they have to go further in their warehouse to find the part that you chose, they charge you what's called an extended component fee. But they only charge you once per type. And that's why, do you remember when I was saying, oh, I don't want 10k resistor, I want a 5.1k resistor.
Yeah.
That seems completely pointless. But that's because it saves me on the extended component fee. And they say $3 per type. So if I had a 10k resistor that was extended for whatever reason, they would have charged me an extra $3. So I must have chosen 24/3, which is whatever, 8 extended components. So they're going to have to send 8 people out into the warehouse to find 8 things, charge me $3, and they'll bring them back to the robots. Then the actual assembly is $1.71. That's the time of robot time, and then reflowing it, soldering it in the oven, and then they build it in 24 hours, and then they ship it to you by DHL, which will charge you, depending on where you live, some unbelievable amount of tax and whatever. So all in, we didn't do LEDs, and I remember the price. I can show you. Oh, I won't show you because I don't want to dox myself. But the one with the LEDs on 2-sided assembly, less well made, as in I didn't make as many good choices. Version 1, if you like, this little guy here, was about $80 for 5. So it wasn't cheap. And then I had to postage, which I think I prepaid tax, and I got overnight delivery. I paid through the nose basically. So I ended up paying £100, I think, all in, door to door delivered, for 5, which is not cheap, but I look at it as like a meal, like a really good meal out, or the joy of a physical thing that you designed arriving in your hand. It's just honestly, it's a magical feeling. People call it JLC day or PCB day, and the box arrives, and here's one from my largest synthesizer project that I haven't even opened yet. Oh. And you pull them out and you get your board, and it's covered in little chips and bits and bobs, and you're like, this is the best thing. It's such a good feeling. So £100, don't know. No, it's a luxury.
It seems reasonable. Like, it's not outrageous, like it's a hobby thing still, but like you need to have this thing produced in China and then shipped over. Like, it's kind of like expected. I would say that it's quite cheap compared to like all the other expenses that you can think for, like Netflix subscription or something like.
Exactly. It's not something you do all the time. It is a luxury, and I'm aware that it's a luxury, but it's surprisingly affordable. Which brings us to the end, which is software. And this is surprisingly short because I haven't written any software yet. But that rolling ball. So I'll do a little demo. Yeah. So we've got a clicky thing goes red. I just coded. So basically, I coded the minimum viable product to test each element of the widget. So it's like LEDs, right? I need to have switched them on and off. Buttons, I need to see whether they're pressed. Screen, I need to see whether I can draw something on it. In this case, it was a small black and white screen. And then accelerometer, I need to be able to measure, the direction of gravity. So that was my goal. And it took me about an hour to write, and it's one C file. So this is not going to take a long time. So this is going to be a very quick thing. Unfortunately, CMake enters the chat. This is where I hate on Raspberry Pi. I don't really hate on Raspberry Pi, but they ship the SDK in source form, which is fantastic. So choose your level. You can choose to just poke registers in the chip to make pins go up and down. And ultimately, that's all you need. You just need a C compiler like GCC or Clang, a debugger if you want to be able to debug, and some memory addresses, and you poke them. And then there's an SDK which they provide, which is very, very thin and very nicely written. So let me give you an example of their.
Can you make it bigger?
Yes, bigger? I can make it bigger. Oh my god. I'm going to look for the word GPIO. Sorry, this is okay. So this is I got fancy with power and stuff. Okay, GPIO.
GPIO init is an example function from the Raspberry Pi SDK, where basically I'm saying one of those GPIO pins, which is on the right-hand side of the chip, and I've made a hash define of button pin. So button pin is pin 23. And if we go and look in my, I've changed it actually. So this is old. This is the old hardware. But pin 23 used to be the first button. And then 23, 24, 25, and 26 were all buttons. So I initialize button pin. I set the direction, meaning is it an input or an output, and is it pulled up? So is there an internal resistor in the chip that pulls it up to the high? So basically when you push the button down, it pulls it down, and when you're not pushing the button, the chip is pulling it up for you. So now you have a pin, and now we can just read that pin. So GPIO get, I think was the function. So somewhere in here, oh yeah, here you go, I've done it with a bit mask. So you can ask to read all 32 pins in one hit, and then I shift it down by whichever was the pin number 23 or whatever, and then I mask out 4 bits because it's 4 buttons, and actually they pull down to ground when you're pressing, so they go to 0 when you're pressing it down. So I XOR it with 15 to flip it back to 1. So now I have a integer that tells me the state of all 4 buttons, and if you look at what this, because they ship it as source, you can just go and see that this is literally SIO hardware is just an alias structure that's in some address in memory. So this literally compiles to a single MOV instruction. So this function GPIO get all is pure sugar, and this literally in Godbolt or whatever would compile down to like MOV return R0 comma some address, job done. And so software wise, there's almost nothing to it. And the most magical bit is the PIO, which I won't talk about yet, but I'll give you a teaser. So, and I'll make that the last thing I do. So let me just see if there's anything simpler. So a slightly intermediate example is the accelerometer. So I built this up myself. So basically the Raspberry Pi provide a library function called I2C. Oh, I've got a kitten. Ishi, say hello to the stream. This is Ishi.
Nice. Hello.
He's up to mischief, and it's like he loves my electronics room because he likes to eat all the electronics. So there's a standard called I2C, which is what the accelerometer uses. And so Raspberry Pi provide a library for using any device that uses the I2C standard. And essentially it's 2 functions. You write to I2C or you read from I2C. Then I went and read the datasheet of this particular accelerometer, and they said, this is how you write to a register on the accelerometer, and this is how you read a register. And it's like just conventions and datasheet. So I literally was reading the datasheet and writing down these functions one by one. They're very, very trivial. Same for the OLED screen. It's like also an I2C device. So it's like if you want to send a command, you do this. If you want to send data flip, display flip, back buffer flip, you send all the bytes, 128 by 64, whatever the size of the screen is. And then the most annoying thing for these chips is that you have to initialize them. So you have to send them a sequence of commands to bring them up because they're like little mini computers themselves. And so again, from the datasheet or from Googling, you can be like, what sequence of magical numbers do I need to send? And literally it just loops over them and sends the commands, and that brings up the display. So that's intermediate. Now the next level and the final level, if you like, is the PIO. So I2C is this standard, right, for electrically talking to things. And there's also SPI, and there's other standards. There's I2S, and I2S is the audio one. So that little chip we added that's the sound card, that standard is called I2S. And before Raspberry Pi, all the vendors would basically license blocks of IP into their chips, and they'd put them in. So you'd buy a chip and you'd be like, this microprocessor has 4 SPIs, 2 I2Cs, 3 I2Ss, 11 UARTs, whatever the hell you want. And part of the specing process would be like, well, I need 3 I2Cs and blah, blah, blah. Raspberry Pi were like, nope. I mean, they do have I2C and SPI, but they were like, we will make a thing called programmable I/O. And it is a thing of extreme beauty. And for anyone who likes PS3 SPUs or something, there are 4 PIOs on the Raspberry Pi, or maybe 8. Let's say 4. I don't know. There's some number around 4 of PIOs. And each PIO can execute a tiny program written in assembler in a completely insane assembly language that I'll get to in a moment. And
that only has 16 instructions in the whole instruction set. So there's like move, jump. It can't even do addition. It can do increment. It can do decrement. It can do compare against 0. It can do a handful of things. And crucially, it can do put thing on pin or multiple pins, and read thing from pin or multiple pins, and send them over to the main to a FIFO of 8 D words big, 832-bit. So it has a teeny tiny 8 D word memory that the CPU can poke into. Is a FIFO arranged as a FIFO, so it can fill up, and it has you read and write pointers and stuff. And so in this tiny instruction language, you can pull off the FIFO or you can push onto the FIFO. And on the other end, the CPU can pull or push from this FIFO. So your only interface to this little thing is a tiny program, and the entire RAM for the program is 16 instructions. So I think you can write a program that is at most 16 instructions long from 16 different instructions, right? And run it. But here's the beautiful thing. It runs 1 clock per cycle per instruction, guaranteed, completely independently of the rest of the chip. So you can use the PIO to program any interface between high-level, inverted commas, ARM land, C land, and pins and wires and electricity and annoying stuff. And so people have used the PIOs to build HDMI ports, which completely should not be possible. That's insane. VGA ports, audio, ITOS. So previously where it was like a zoo of peripherals.
Yeah.
Now, so we're actually using the PIO for one thing, which is the LED. So do you remember I said short pulse or long pulse, right? And then to make the LED, to send it a 1, you send it a long pulse, and send it a 0, you send it a short pulse. And then when you're done, you just stay silent. So guess what? Raspberry Pi, thank you, in 2020, they provided, let me see if I can make this bigger. They provided a sample program of how to program. They have a little assembler. So this is a DSL. It's not C anymore. And this is a hash define. God knows why they chose this syntax, but basically hash define T1 is 3. That's the length of 3 cycles. We'll see why in a minute. This is another 3 cycle instead of 4 cycle. And I think they have a Python compiler or something, or it can spit out Python for like MicroPython. So whatever, I don't care about that. Here's our program. So this is our entire program for this tiny little processor. And I'm going to explain every instruction in just a moment because it's kind of fascinating. And then they have a helper, which is that you can just say, here is my binding code. So it's like a shader. These are like the world's tiniest shaders, basically. And this is just a little block of C code that basically configures the PIO and loads the program into it. So it basically sets up various, doesn't matter, sets up the FIFO, sets up config shit, basically, and then says, right, we're ready to go. Now, this program is just a thing of beauty. So instructions are insane.
Do we do it now, or do we do it on a software stream?
We do it on the software stream, but I will just describe this one instruction then, just to give you a taste. This one instruction out grabs a value from the FIFO. So the CPU has put a color into the FIFO. So like RGB value of red, green, blue. So Mr. C programmer Alex has put FF00FF into and I've poked it into the FIFO of this little GPU, this tiny little shader. This pulls 1 bit of it. So like this instruction out, I don't know why it's called out, it's really badly named, but it grabs from the CPU.
It's actually kind of in.
I think it's out from the perspective of coming out of our chip. This is going to go to an LED. So the direction of travel of information is out of the chip. But we're grabbing from C land 1 bit. That's what the 1 is. And we're putting it into our register X. Oh, by the way, we have 2 registers. This CPU, this micro CPU has X and Y. Those are the only 2 registers available. So if you thought x86 was constrained. So yeah, we've grabbed 1 bit into X. Meanwhile, we have what's called a side set pin, which is actually the main pin, and we want to set that pin to 0. And this is a VLIW processor, so basically encoded in the instruction, we can say set one of the pins to 0. Then in square brackets, you say how long you'd like to wait for in cycles before doing the next instruction. So this is please wait for
T3 minus 1. So please wait for 3 cycles on top of the cycle that you already just spent doing the out. So in other words, the reason they've written it this way is because this whole line is guaranteed to take precisely
4 cycles.
4 cycles.
Yeah.
And while those 4 cycles are happening, the pin is 0, the LED is seeing 0. Then we say if X is not 0, or if X is 0, we jump to the do 0. Otherwise, we fall through to do 1. And you can see where this is going. While doing that jump, we set the thing high. And if we're doing a 0, we immediately set it low again. Or if we're doing a 1, we stay high. So this is the entire long pulse, short pulse expressed in 1, 2, 3, 4 instructions, one of which is a NOP, hilariously. So the whole convention of that LED that was made up by somebody in an LED company, other chips have to make an LED peripheral and bake it into their silicon. But the PIO allows us to have these microscopic programs that capture the electrical spec in software terms. So that's the
that's crazy.
That's the PIO. Yeah, it's cool, isn't it? But in the end, you don't have to think about it. So back in C-land, you just say LED PIO push or something. Oh, I can't find the line. Text is too large. Here you go.
Put blocking. Yeah.
Put blocking. So there are 4 PIOs. We use the 0th one. If the button is down, put that color into it. And the LED, for some bizarre reason, it's big endian to start with, so it shifts the bit out from the top. So 24 bits, but from the top, so I have to shift up by 8. All these little gotchas. It doesn't really matter, but like, and this is the color. This is actually purple for my daughter. She wants a purple one. Okay. So blue is high, green is a little bit, and maybe cyan. It's like a little turquoise thing. But the one I have was red. So the previous, this was FF. Red would be that. And then we have red. And so yeah, that's nice. So we've gone on the full journey. We've gone from resistors and current to C.
This is perfect. This is awesome. Okay.
Yeah.
Nice. So this was like part 1 of our little series. And ideally we send the design like off stream to China. I'll post the links on X with the live
GitHub
preview what is happening in the factory level, right? Because
that's with my login, but I will occasionally post the
maybe like a screenshot that like the wooden docs you or something.
Yeah, exactly. And I will put on GitHub the state of the design files as they are today. There's probably bugs. So basically the thing I showed you that we reviewed isn't done. That was me saying, okay, I don't want a black and white screen. I want this color screen. And I started sketching that out, but it's still got unfinished, there are wires that aren't connected and stuff, but I don't care. I'll put it up into a repo and you can all tell me all the bugs I have before I spend money. And then in like 24 hours or so, or maybe 48 hours, I don't know, I'll spend $100 to get them ordered, and we'll wait a week, and then we'll write the software and we'll bring them up. Nice. Which will be scary. If anyone has any ideas for what, so the spec is 4 buttons, 4 LEDs, accelerometer. It's got a sound card now. This one didn't, but this one will have 16-bit, quite high quality audio that we can solder a speaker to, and it will have a 240 by 240 16-bit color. If I can make it, so this is a physical thing. This little thing, if I can make it wake up, is a square display. It doesn't look square, but the visible, if it lit up, it's square. It's I was thinking actually we could, but the frame buffer would use up half our RAM to give you a sense of like how small, like 2 bytes per pixel times more or less 64K pixels is 128K. We only have 256K of RAM. So probably we want to do it scan line by scan line, so we won't have to think about that. But I was thinking we could have a frame buffer that's half res and do chunky pixels, 120 by 120, and maybe do 16 colors and do like the Pico 8 type palette or something. Anyway, we can write a little bit of C that on the fly converts from whatever pixel format to the and then sends it down the wire to draw the screen. It'll be a bit slow, but it'll be fine. So we can have 240 by 240 or 120 by 120
16-bit color or less, doesn't matter.
Nice.
That's what we'll have in our hands in a few weeks' time.
In a few weeks' time we can figure out in the background in the Discord or X.
Yeah.
Like what's the great game that we're gonna put on there? A game or like an application.
As a funny software thing to end up, like when I brought the screen up, I didn't mention what I did for the software. My daughter really loves. Oh, it switches off after 10 seconds. My daughter really loves balancing the ball in the middle. Like it's really sensitive. So you can actually use this as a spirit level. I realized it's sensitive enough that you could actually like change the code to draw a dot, where down is, and you can actually use it as a digital spirit level. But what I love about it is it's an SDF. So the way the physics engine TM is literally now we're in game coding land. It's like home territory. Everybody, we're home. We can do gaming. Here's the ball.
SDF. This little dot.
Yeah. So ball X and Y velocity. That's damping. That's accelerate the ball by the value read from the accelerometer. Moves the ball, bounce it off the edges of the screen. Pretty dumb. And here we go. Loop over the pixels. 128 by 32 screen. And you have to loop in 8-bit. Like the pixels are not laid out in raster order because they're bastards, but don't worry about that. And then this is the distance from this pixel from the ball.
Oh, wait, can you say it again? They're not laid out in a raster order, meaning in what order they are?
They're on this particular screen, which we're going to switch screens, this won't apply, but on this particular screen, each byte is 8 pixels vertically. Then the next byte is horizontally across from there. So you basically get a line
You're kidding me.
That's fine. You just have to. So I build it up. So if you look, I loop over the Y in jumps of 8. Then I loop over the X properly. And then I loop within the Y, within the 8, in order to build up my byte, my monochrome 1-bit byte. This is the distance of the pixel from the center of the ball. This is the squared distance. And if the squared distance is less than 1500 squared, it's an 8-bit fixed point. So what's 1500 over 256? 5.8 pixels big ball. Then I set the bit and I write it into the... I was going to do a logo. I was going to do a Wookash logo, but I didn't do a logo. I did a bouncing ball in the end. Wrote it into the logo buffer and then flip it. So I managed to squeeze an SDF into a renderer into the ball. But
Nice.
hopefully that gives people some inspiration, because I have no ideas what we want to do with this thing when it arrives. So hopefully people are, and I hope that was enjoyable and not too obscure. My biggest happiness would be if one person who watches the stream dares to go and make a thing, and I'm sure it won't be like this thing, but like goes, someone who's never done hardware before goes, that didn't look that hard. I'm gonna have a go, and I really recommend it. It's really rewarding. So there you go.
For me, it was like we went from like I will never ever do that, like I wouldn't want to even touch that like area, into like, hey, this is like thing that is manageable. Like I just seen it. It's just like steps you need to do, and you can do it. Like that's
and it's really crazy that like so everything I showed you today. So the synth I made in COVID is this thing here, and it's open source now. So I'm not shilling. You can download the files for this and the software and the hardware. It's all open source on my Plinky Synth GitHub. And there's nothing in the manufacturing of this that wasn't in the stream that we just did. There's a bit more analog electronics and a bit more like different parts I chose because it was 5 years ago. So I'd make different choices today, but it's wild to me that everything I showed you today is enough. It's not enough to become an electronics wizard. I couldn't make a GPU to save my life, but you can do a hell of a lot, and you can make viable products that sell, that make people happy, just with what we did in the last 2.5 hours, which is
that's PlinkySynth.com for everybody who's listening.
Yeah, so there's the logo back to front. But PlinkySynth.com. And it's open source, so you don't need to go and give me money. In fact, it's not made by me anymore anyway. It's made by a lovely German couple. So I don't even benefit if you do buy it. But it's wonderful to me that people could make physical things. And there is something joyous in holding something in your hand that is sort of, it's the same as 3D printing. If you've ever had the experience of 3D printing, and that moment where you're like, I made this, I designed this, and now it's physically in the world. It's that same feeling, but with computers.
Nice.
Yeah.
For everybody who is listening, this was part 1. There's going to be part 2 when we're going to program the actual thing when it arrives, creates the stream. This stream will be available for members in this like raw, unedited fashion. And I will spend a couple of weeks edit this and then fit in the schedule, and like high quality, improved audio stuff and video will be released in a couple of weeks. And that's it, I think.
Yeah. Amazing. Thank you so much for the invitation to.
Thank you, Alex, for coming on.
Hope it was fun.